Because
Why is there spontaneous emission?
the energy state is not stable. You have another available state that's more stable. I mean, if the atom is in excited state.
Okay, but but that doesn't explain how the Schrodinger equation knows to do it.
Or let's say in equilibrium you should have more number of electrons in lower states. So that's now equilibrium.
But the Schrodinger equation doesn't know that.
Schrodinger equation doesn't know that, but
the Schrodinger equation only knows that if you have an eigenstate of energy, it stays in that eigenstate.
But if you have perturbation, then.
So why is an excited state of an atom not in an eigenstate?
Well, it is an eigenstate.
No, if it were a true eigenstate to all orders of perturbation theory, it would not change.
Yeah.
But obviously it de-excites.
Yes.
So what in the Hamiltonian is causing it to de-excite?
In the Hamiltonian?
Because of the uncertainty.
No. The point is that you have to consider all possible states in the Hilbert space.
Yeah.
And one state in the Hilbert space is an atom in an excited state. Another state in the Hilbert space, in the same Hilbert space, is an atom that's de-excited.
Yeah.
But there's one photon. That's a possible state in the Hilbert space. Now, if you don't include the electromagnetic field, then the 2p state is an eigenstate of the Hamiltonian.
Yeah.
Because there's no electric field. When you had quantum mechanics, did they teach you the transition probabilities?
Yes.
But that's if there's an electric field there.
Yes.
Now, suppose there's no electric field. You're in total vacuum. So according to the formulas they taught you, there should be no de-excitation because E equals 0.
Yeah.
So there's no off-diagonal term.
Yes.
So why is there spontaneous emission? And it's because if you include photons in the Hilbert space, then even though there's no electric field, there's some other state in the Hilbert space where there is an electric field, namely where there's one photon. And it has the same energy as the original state, because a de-excited atom plus the photon has the same energy as the excited state without the photon. So even though the electric field is 0, if you properly consider the Hilbert space, there's some other state in the Hilbert space that did have an electric field, and the Hamiltonian, written in terms of creation and destruction operators, is an off-diagonal term that couples one to the other. It operates on the electron. It's the right.
So basically,
it's we have two states, X and Y. X is excited state and photons. Sorry.
No.
X is
n plus 1.
the excited state, and Y is the excited state with n photons. But n could be 0. So let's. So Y doesn't have an electric field, but there's a term in the Hamiltonian. Unfortunately, I can't. There's a term in the Hamiltonian. term in the Hamiltonian, J mu A mu, and J mu, if I'm not mistaken, is phi bar gamma mu phi, where this is an electron
Yeah.
creation operator and this is an electron destruction operator. And A is the electromagnetic field.
Phi.
So it creates a photon and it actually there's already an electron, so it can destroy an electron and recreate it, or it can make a second electron and destroy it. But the point is there is a term in correctly quantized QED that couples states X and Y. So even though there's no electric field in state Y, there is an off-diagonal term. So now the question is,
And that's coming just from the vacuum fluctuation?
that's my question. Is it coming from the vacuum fluctuation, or is it coming from the photon that will, look, it's coming from this term in the Hamiltonian, or the Lagrangian, actually. But my question in practice is, it coming from the vacuum fluctuation, which is actually half a photon, or is it coming, or maybe it has nothing to do with the vacuum fluctuation, because I didn't say anything about vacuum fluctuation when they connected X and Y.
Mm-hmm.
So, but the way to formulate the question is, what is the rate of spontaneous emission? How many photons does it correspond to?
One photon.
Yes. And if it were the vacuum fluctuation, it would be half a photon,
Yes.
right? So,
Why now?
because vacuum fluctuations contain half H bar omega,
Yeah.
and not, they have half a photon in them.
Yeah. Sure.
So I claim that, unlike what you often hear, the rate of spontaneous emission is just the stimulated emission that you would get from one photon and not from half a photon. Now, Einstein did that with Boltzmann coefficients, the whole rigmarole. But I think, with all due respect to Einstein, that was unnecessarily complicated. How do you tell immediately that it's one photon and not and not half a photon? You simply note that in thermodynamic equilibrium, the two states X and Y are equally populated, or any two given states where the photon is in a well-defined state, and therefore the rate at which it goes from X to Y is equal to the rate at which it goes from Y to X, because the Hamiltonian's Hermitian, and the same off-diagonal element takes you one way as the other way.
Yeah.
Now, except that we're talking about microstates, and there may be a lot of different states of the photon, so the rate of spontaneous emission is the sum of the rates to all the different photon states at the same energy. And that's how you is this the end?
The first page.
This is the first page.
Well, do we have?
Yeah.
Did
we
you
have
copy more?
Here a PDF. No, I didn't copy it. Just copy one.
So this is the PDF,
Yeah.
and this is the second page.
Yes.
And how do I copy?
Yeah, I can do that.
What? Edit?
You tap somewhere
And then
at the beginning.
Edit.
and then copy that.
Take a snapshot. Do I need a
Yeah.
snapshot?
It's already in snapshot mode. So you tap somewhere in the right top corner, the left top corner of page 2.
But you can copy the whole one and then paste that and everything.
No, I
will be-
couldn't do that.
He
I-
tried and he couldn't. I said take a snapshot.
Yeah.
But
Tap somewhere.
But it's
Tap.
Maybe
no,
double
but
tap.
it's not taking a snapshot.
Maybe double tap. No.
You do it.
It's not selecting.
The problem is this is a lousy tablet.
And it's
Tablets sound very nice, but
Yeah.
not only if they're good. And this is lousy.
Maybe
Google
let me go
Access.
to
What?
let me go to computer mode and then I know.
You know what? I want a mouse.
I know it's not working.
Control A, Control A and select all. Yeah,
It
there
didn't
you
work
go.
for me.
Control C. That's all.
Do I have a mouse?
Control V.
Yeah, I have a mouse.
Copy the same thing.
Yeah, no, everything is
No,
correct.
oh,
Everything is
second
correct.
Okay, second page.
Oh, this is the second one. Yes.
Do the third page while you're at it. You're on a roll.
Can you stop that so I can do something?
Okay.
Control, Conceal, Alt V.
Okay. So you have 3 pages.
No.
Third one.
I know. I'm going back up. Okay, so what I do is I do the Einstein calculation, detailed balance. Instead, but I just use 2 microstates because detailed balance means I can use any 2 I don't have to use the Planck's formula for black body radiation. And basically, I said that I just postulated that the spontaneous emission rate is R, where the stimulated emission rate is R times N, where N is the number of photons. And then here's where the Boltzmann factor comes in. The system by itself has a Boltzmann factor relating population of states A and B. And n is the expected number of photons in the same state, which I also use just using thermodynamics and statistics. And this is how you calculate the expected number of photons of bosons in a state. And then I make sure that the net absorption rate equals the net emission rate, and I find that it does. No, so this is an explicit derivation using Boltzmann's factors. What we said before, that that the rate of spontaneous emission is exactly what a single photon would stimulate. Okay, now to get the total rate, you have to figure out the density of states in the box. And here also, it's standard thing. It's in Rybak and Lightman, except I think if Rybak and Lightman, if there's any mistake in that book, it may be here. I actually asked Alan Lightman once when I saw him. I said, I thought maybe there was a factor of 2 error in the black body cup. But the point is, I think the subtlety is that you have to know that for a standing mode, you're talking about real photons and standing modes, and minus k and k are the same standing mode. And I think if you do that, if you remember that, then you get the black body formula exactly right, instead of being off by a factor of 2.
Why is it factor of 2? Because of the two polarizations?
Oh yeah, the two polarizations. But there's only one quadrant in K. I think K and minus K represent the same state. I'm not saying that if I just flip Kx and Ky, I'm not sure that's the same state.
No, I think so. Relative sign.
But wait.
So
No. See, if you let K go to minus K, you get minus. You might get minus the answer, but the point is, it's oscillating. It's equivalent to a phase shift.
So something is the relative sign between Kx and omega t. It's plus or minus.
Right. That part.
So
that part is important because that part is very important. For a given omega, minus k propagates one way and plus k propagates the other way. But when you have a box with metallic walls and it's fixed modes, I think you have to assume that they're standing modes,
So
and the two modes going opposite have to interfere. So it's really only one mode.
Yes.
Now there's an interesting there was an interesting bit of history, K and minus K.
But you can still accommodate 2 photons, right? 2 states, left moving, right moving, in one standing mode.
No, I think it's only one state. When you calculate, it's one photon, but the state is a superposition, and that's the only one you're allowed. The box does not allow, the other phase shifter or the other. But it does allow. Well, it allows phase shifts in time. If you wait half a cycle, you'll get the other configurators, but it's still only one mode.
Okay.
Anyway, when the density of states in the box, it's 1 per pi over L cubed. As because going from 0 to L, the whoops. Wait a minute. Draw. Why do I have to do this every time I want to draw? Anyway, to go from here to here, it's only pi. It's not 2 pi. And then if you do this, that's 2 pi. And then if you do this, no, it's 3 pi. So you're getting 1 per pi, not 1 per 2 pi, not 1 per pi, but, and then it's 1 per pi over L cubed, because each direction it's constrained to be, and then there are 2 polarizations. So if I do that correctly, I get 8 pi cubed, and the number of states, all the pi's are all there, but the point is there's an 8 pi on top. And I'm pretty sure that 8 pi is correct.
Yes, correct.
Yeah.
4 pi times 2.
Okay. And of course, when phi b is greater than phi a, there's a population inversion, and n can grow indefinitely because temperature is basically more than infinity, and even in thermodynamics, there's no limit. If you have an infinite temperature, there's no limit to how many photons. So that's what a laser is. And okay, that's the end of lecture 1, I guess. Now,
No, lecture 1. We also have lecture 1.
what?
There are more.
Can I go down further? Yeah, but that's the end of that. See, we can move fast in this course because I give the notes ahead of time. Now, there doesn't seem to have been any. Okay, the next lecture is Bremsstrahlung. Now, you should. Did you learn Bremsstrahlung in lecture then?
Little. Just revise right now.
Okay, so we'll do it. So this is the PDF file. I still can't write on it yet, can I?
Can you double click?
Yeah.
Double click where?
Anywhere.
Or Control A should also.
Try Control. No, you're on the keyboard there.
Right click, select all. Yeah. There you go. Copy.
Oh.
Right click, C. Copy selected graphics. And then paste
Oops.
there.
Did I do that right?
Select all. Copy selected graphics. Then paste there.
Paste where?
And there is word or somewhere where you were working.
No, I have to go back.
The third icon in the.
Here.
Yeah. Paste there. Control V or paste. Just simply right click and paste. Paste all.
Paste options.
Yeah, there's an icon there, just below the paste option.
What?
Just below the paste option, there's an icon there. Yeah, click on that.
Did I get it?
Yes.
Yeah, you got it, but you have to adjust the position.
You can expand it. Click on the image. You double click on the text.
Yeah. Then you
drag it.
diagonally.
Okay, this is the sort of thing I'd like you to do when I ask you to put the lecture on this computer.
Okay.
But you have to take it left, your left, because something is hidden in the right.
Yeah.
So you tap there and then just take it. Yeah.
Okay. Never mind. All right. Basically, first thing you have to do in astrophysics is be able to make an order of magnitude estimate. What's the maximum frequency out to which Bremsstrahlung is efficient? How do an electron hits a proton, how do I figure out what the maximum frequency is? Let's say I give you the impact parameter,
Yeah.
B. So what's the maximum frequency?
H mu is half mv square. So H mu electron.
And the time period will be
Just tell me in
calculated.
words what the idea is.
Yes. B by V.
No, if you're writing, I don't even want to.
Okay.
Just tell me the basic idea before you write anything. You have to know what you're going to write.
So the kinetic energy.
Look,
It cannot be smaller than.
So I can calculate the kinetic energy and equate it with the potential energy and then find the V, and from the V
well,
we can.
the potential energy between.
This particle, this electron or something.
Yeah.
And then find the V, and then from that the time period 2 pi B by V. B is if the short distance between them.
Wait a minute. What's V?
The velocity at the shortest time, shortest distance at that point.
Well, okay. But it's the velocity of the electron.
Yeah.
But that's, let's say it's of order of the thermal velocity. Actually, what you're saying is it could gain more velocity if it fell in.
Yeah.
But it turns out that that's true, except that it turns out it doesn't matter. But in order to explain why it doesn't matter, let's wait. But for any points, for any impact parameter and velocity, the characteristic time scale is b over v, right? So which means that the minimum period of the light is that, and the frequency is v over b. That's the maximum frequency.
Yeah, sure. That's what I'm thinking.
There is a minimum frequency.
There's no, well, let's put it this way: if you have a pulse of acceleration, and the power spectrum is the Fourier transform in time of that pulse, and what's the Fourier transform of the delta function?
It's constant.
Yeah, so there's no minimum.
Yeah.
The minimum will get. No, even there's no minimum.
There's no minimum.
There's no minimum for Bremsstrahlung. Other things may impose a minimum, like propagation or escape, but in principle there's no minimum, and Bremsstrahlung photons should be in thermal equilibrium. Even if they can't get out, there's some level of thermal equilibrium. So, yeah, I mean, you can have free emission that's radio waves. No reason why not, which is very low frequency, but okay, now this is the calculation for radiated energy. This is what you get from Jackson, and it's basically the proportional to beta dot and geometric terms. And the pulse width is 1 over tau, so this is what I said before. The power spectrum is going to be this integral. Wait a minute, there should be a
R. Oh,
no. Here, I'm assuming that e to the I omega t is of order unity is equal to 1 because omega is
very less.
Is small.
Very small.
Over the time scale where this integrand changes. So then it's easy to calculate. And the opposite extreme, you assume that the oscillations of e to the I omega t are canceling out the, since it's varying a lot over, and this is varying very slowly, it's exponentially small. Any Fourier transform of a slowly varying thing is exponentially small in omega. Okay, now I need more.
Select one. Copy. Selected.
And now I want to go, just a second, I want to go back to here. Oops. Okay. Now, delta beta, this is just the change in velocity because I integrated acceleration over time and I got roughly the change in beta. So how do I figure out the change in beta? Well, that's delta V. The change in V is just this integral. And there's a trick for doing this integral. It's Gauss's law. Because it's just the perpendicular electric field operating on the cylinder. If you took the trajectory and rotated, multiplied by 2 pi, you get a cylinder. So you just use Gauss's law on the cylinder, which is 2 pi times the impact diameter in area, and so you get the delta V is just this, and then you get this expression for how much energy was emitting. How much power was emitted per unit omega for a given impact parameter.
This is approximate version of delta V.
Delta V, approximately. Well, actually no. It's a very good approximation. Gauss's law is exact.
Yes.
And I assume the straight line trajectory instead of taking into account the curve.
Yeah, so you're taking it on the curve.
Okay, Rahul, approximately. chapter 1?
Yes.
Where do I get the stupid keyboard?
I think
I want a tablet with a
when
keyboard.
you tap on the field where you write, it will appear. Oh yeah, it did appear. No, you.
There we go. Alright, what do I want to call this chapter 1? Lecture 1. Now, this is I need an apple here. Okay, now you define a radiation cross-section, which is, this was for a given impact parameter. Now, no, that's just the amount of radiation, but now I want to multiply it by area, so I get what's a radiation cross-section, which is the area weighted by the amount of radiation. And when it finally has units of area, it will be as if it had a disk of a given area times the average value of radiation over that disk. So you can just think of it as being a finite area, and each time you get the same amount of radiation. Can you make sure that's on? I thought I turned it on. Hit the on button, and the green light should go on. Yeah, it's on. Where did it go off? Okay, so now here you notice that it's logarithmically divergent.
Yeah.
Because when I multiply by b, I get an integral portion of b. Now that's well known. It's well known that even if you computed it with field theory, or even if you did it classically with the Rutherford scattering cross section, the distant encounters give a little bit of deflection. It's a 1 over r squared force. That's what they mean by an extended, a long-range force. They mean at least the slow is 1 over r squared, which means when you multiply by r, you get 1 over r, and when you integrate, it's logarithmically divergent. But the other way they get is that the number of photons you get per collision in quantum mechanics is logarithmically divergent. The amount of energy you get is finite, but since there's no limit to how low the energy of the photon is, the average energy of the emitted photon is 0 in Bremsstrahlung, and you get a logarithmically divergent number of photons. Most of them are very soft.
So I didn't get that. Why that divergence? Why the average is 0?
Because you get a finite energy radiated per collision, but you get an infinite number of photons. Because the impact parameter can be large, and that means you get a lot of soft photons. In other words, you get in each energy range, you get about 1 photon.
That's true for any power law.
No, for each logarithmic range in energy, you get about 1 photon. It's not true of any power law, but it's true of one particular power law where you have equal number of photons per law. Now, in the soft omega, there's very little energy there. It's it's only one photon, but the energy is proportional to nu. So the integral d log nu times nu converges. Or h nu times d log nu converges. But just 1 per d log nu is logarithm of theta. Now that sounds just like a mathematical technicality, but it's actually very bothersome when you build a detector and you want to measure the energy of a photon. Like, suppose you want to measure the energy of a gamma ray. Well, you can have the gamma ray pair produce and then measure the energy in the electrons, photon. It's just that when you pair produce, you can also pair produce with an extra photon produced, or it's just a Bremsstrahlin correction to the pair that's produced. You can just add what does pair production look like? It looks like this. But then you can get, when you pair produce, you can get sometimes an extra soft photon being blown off. And even though the fine structure constant is small, even though this is a perturbative correction, this photon can be arbitrarily soft, so it gives an unlimited number of photons, each one softer than the next. So if you want to have really good energy resolution, like 1%, you have to worry about that photon with 1% of the energy that was, it's soft. You're not going to detect it, but it's just basically missing. So if you use calorimetry to detect, the heat deposited by the pair, there's a good chance you lost some in soft photons, which you can't correct for. So it actually does limit. It actually is a pain in the neck for experimentalists. So these soft Bremsstrahlin photons. And but the one thing they're good for is if you want to, if you, like in a gamma ray burst, come in.
Sorry, welcome back.
Yeah. In the gamma ray burst, you there's a lot of photon entropy, I can tell you, and some models are actually wrong because they assume black body radiation. They assume a photosphere, say 10 to the 12 centimeters of gamma rays, and they assume that it's emitting like a black body there. But actually, if you carefully calculate, you find what makes photons. You need a process to actually make new photons, and you can rely on Bremsstrahlin. And Bremsstrahlin, if you just use these cross sections, might not be enough. If you count the soft photons and assume that they'll be Compton upscattered by, that they'll gain a lot of energy by Compton scattering, that's okay. But the point is, there are certain situations in astrophysics where the optical depth is large. The probability for a photon scattering off an electron is large, but the probability for making a new photon is small. Now, typically, what they say is it's down by 1 over alpha. Like radiative correction where you make a new photon is. Well, let's now say that this is a Compton scattering. Okay, so the photon scatters off an electron now, and it's Compton scattering, which upscattered this photon. That's fine for increasing the energy of existing photons, but it's not the same as making a new photon. The problem for making a new photon, I think, is probably down by a factor of alpha, which is about 1 over 137. Except that if you count all the soft photons, you get a log factor. If you just count the photons, because it's logarithmically divergent.
So what is that alpha you told?
Alpha is the fine structure constant.
Okay.
It's E squared over H, and it's 1 over 137. Okay. So, anyway, but we're still at radiation cross-section here.
Again, I didn't get what's the problem with black-body radiation here?
That you can have a high optical length and still not get a black body photosphere, because the time to make enough photons required by the black body limit is not enough. Like in gamma ray bursts, for example, suppose the photons were made like near the black hole, and then they expand. The idea is if they're made near the black hole, you'd never expect to see them because of the photon opacity. You might see photons that are below the pair production threshold, but if it was too close to the black hole, even the black body limit wouldn't give you enough photons. And it's actually a good calculation to do. You know what? I think I'll assign you this homework. Calculate a gamma ray burst has 10 to the 57 photons in it. And the temperature is, let's say, well, to make it interesting, let's say the observed temperature is 100 keV, because the peak is typically at 300 keV. So if it's a thermal spectrum, it's 100 keV. What's the minimum radius? Yeah, I'm assigning this for homework. Okay. Gamma ray burst peaks at 300 keV. If it is thermal, what is T? And I'm telling you now it's 100 keV, so it's around because the Wien peak is back. And now for the big question: what is the minimum radius for making this number of photons wait a minute, A, all at once, or B, and I'll tell you it's going to be slightly easier, within 30 seconds, which is typical duration of a long gamma ray burst.
So this should be 100 kV you told, this thermal.
What?
The peak is at 300.
Yeah, so the temperature is at 100. But then I have an expression for black body photon entropy. And the point is, it's much bigger than the black hole. And so the standard picture that's evolved for gamma ray burst is that well, you don't make the photons near the black hole. You have this outflow of baryons, and you finally see them when the optical depth of the baryons is of order unity.
Mm-hmm.
And let's say they invoke shocks to get shock heating at radii of 10 to, it turns out it's 10 to the 12th centimeters roughly, or even more, depending on what you assume. Remember, you need a minimum energy for a gamma ray burst. You need a total energy of at least well, 10 to the 51 ergs, but let's say at least 10 to the 50.5 ergs. So you need a lot of baryons to carry out all that energy. And, you know, of course, the higher the Lorentz factor, the easier it is. But now do the calculation. How many baryons do I need to carry this energy? Well, the answer depends on gamma, but it's this divided by gamma, mc squared. That's the number. And at what radii would those baryons become optically thin? You know what? Here's another homework problem. At what radius would 10 and 51 over gamma mpc squared let's call it n just so you'll become transparent. Great.
To which energy?
To Thomson scattering. Transparent to photons. Anyway, you'll find that it's much larger than the it's much larger okay, now I have one more question. You take this energy, let's say
Which energy, sir?
ten and 51 ergs. Actually, this 10 and 51 had units of ergs. At what radius would the temperature fall to 100 keV if there are 10 to 51 ergs total. So you do these three problems, you'll understand why gamma ray bursts are interesting. Because you'll find that you'll prove that gamma ray bursts are impossible if you do these three questions. And to really understand why gamma ray bursts are interesting, and to really be motivated to research, it makes a great homework problem for first year radiation, for simple radiation. It's just basic thermodynamics. And the point is that the radius at which it becomes transparent is far greater than the radius at which it's hot enough to. So there is one way out. At what value of gamma, which is the bulk amount of energy per proton, would 2 and 3 agree? Okay, I mean this is important stuff. Since it's basic thermodynamics, I don't think it's particularly long problem set. Except for there is one tricky thing, which is that since the thing is moving relativistically, you have to calculate optical depth not in terms spatially, but in terms of time, because it's expanding at c. And
expanding with c.
The matter of the gamma ray burst, let's say, is expanding at c, or close to c. And the photons are the density you see as the outside observer is not the same density the photons see. And the time you see is not the same time that they see. So from a photon's point of view, you have to ask what's the probability of scattering before the density increases before the density decreases significantly, because the density in an expanding shell is constantly decreasing. In other words, the photon is let's say there's an outflow, so the photon is constantly moving outward also. And it's constantly finding itself in a region of lower density, which goes as actually at least it's 1 over t squared, because it's 1 over r squared.
Yes.
And things moving at c. So well, I think you must have done the first year you were here. You probably did calculations like that.
Yes, I did.
Yeah. So you know about relativistic effects, but you need to do this for the research anyway. So you're killing two birds with one stone. Anyway, so now here's the point. People say, well, if we assume a gamma that's large enough, we can get them to agree. The problem is when they want to make a photosphere at this radius, which is large, the density is already very small. And there's not enough time to make new photons. There's enough time to scatter old ones, but there's not enough time to make new ones because the rate is down by a factor of alpha. And the thing is, it's only down by a factor of alpha times some logarithmic factor because of the soft photon. So it's not quite as bad as alpha, but it's so so I always try to, if doing something basic, I always try to show an astrophysical application. What time is it? How long? It's been an hour so far?
Yeah.
Okay, well that's not enough. So let me finish this whole business on Bremsstrahlung. Ah, yes. Okay. Okay. Anyway, getting back to this logarithmic divergence, we have to do something about it. Uh-oh. Am I missing something here? Oh, I may have a little too big. Okay, so logarithmic divergence means you have to establish a realistic B min and B max. So B min is established by the fact that we made an assumption. We made an assumption that B was well defined, that was a classical trajectory. In fact, the uncertainty principle in quantum mechanics gives you the minimum B because we want the direction to be fixed. So it means delta P has to be smaller than P, and that means that delta X for that upper limit on delta P, it's a lower limit on delta X. And
H goes by
now, to say this would simply be to say that the orbit is greatly disturbed by nuclear attraction. This is the B min at which the assumption of a straight line trajectory is no good. But there's another constraint from quantum mechanics that B min has to be H over mv. So that delta P, which is H over B, is no bigger than mv, which is the original momentum. And that's being pretty generous. That's saying the uncertainty could be comparable. You could produces a 45-degree. Anyway, it turns out that this is more stringent than this because generally it's HV over ZE squared. That's the ratio of quantum mechanical to.
But you're also assuming the electrons are not trapped by ions.
Wait, I'm going to get to that. No. It's the electron scattering off the ion. The nucleus
Yes.
is charged Z. And if it were if the thing perturbed the electron a lot and not just a little, then my whole assumption of Gauss's law and constant V, my whole derivation would have been incorrect. But the point is that if beta is greater than alpha, in other words, if the electron velocity is greater than c over 137, then this becomes the more important. If it's less, then it means the electron is very slow, and even classically it'll be perturbed a lot. But if it's going fast, then it would whiz right by, in a straight line. And basically, beta equals alpha is roughly what you have in the Bohr atom. So if it's moving slower than the electron in the Bohr atom, it gets captured. You can't assume the Born approximation, which is that it just whizzes by. But when it just whizzes by, it means that this is the more important constraint on Beeman. It's actually the greater impact parameter. So it's basically that the electron is unbound. But in Bremsstrahlung, we're considering electrons that are usually unbound. Otherwise, if for cooler plasma, we'd be considering bound-free emission, which is stronger than Bremsstrahlung. But it's a different formula, and there's a lot of atomic physics that goes into calculating it. And another way to get the quantum mechanical limit is to say that the maximum omega, remember there was a maximum from the time of the collision, has to be less than the kinetic energy of the electron, and that gives you the same limit as the uncertainty principle. So the log term should actually be okay. Now here, this should be an h bar omega and not an h bar w. You have the tech file, the LaTeX file.
Well, it looks similar, so maybe I missed it.
What? Yeah, no, I'm not blaming it. I mean, I missed it. I wrote these notes 30 years ago. I've been missing it for 30 years.
I'll change.
You have the LaTeX file? Okay.
I'll
You change it.
I'll change.
And you can add the homework into the LaTeX file.
Yeah. Okay. This one I'll do.
Just so it'll be there for future generations.
Sure.
Now, what was the log term in phi? I forgot. It was log B min. Yeah, because the assumption is there should also be a B max here.
But B max is V by U.
B max will probably be the separation between two.
Yes.
Still, it's well, if it turns out that it's less than B min, I mean there are two terms in this log. It's one minus the other. But if B max, if it turns out that that's
you have this V over omega.
Yeah. V over
V plus B max.
V over omega. Yeah, that's an omega. No, that's just to give B
That's
min
V max.
units, dimensionless units.
What was B max?
No, the point is if there's going to be, it's going to be
Oh, you have also
one.
got
It's
B max.
just
V over omega.
just a second. It's going to be log of B min to the minus 1 minus log of B max to the minus 1, right?
Yeah, so
But if B max is much bigger than B min, then B max to the minus 1 is much smaller than B min to the minus 1. So that's why I ignored the second term.
I don't think you have ignored. You simply
So why
difference of
what,
two log is
Well,
log.
wait a minute, what?
log a minus b is log a by b. Log a minus log b is log a by b. So it's fine.
Oh, I'm sorry. B max is
V by omega.
B max is the V over omega.
Yeah.
Okay, so this is correct.
Initially we started with that.
Right. Because we're still working at a given omega.
Yes.
Eventually I'll integrate over, but we're still at a given omega. Yeah. So B max is. Okay, so now that I've established B min from quantum mechanics, then I have my answer. And it involves so I of omega B was just well, sorry. The radiation cross section is this. Maybe that's another mistake. I wrote I here. I think I meant chi here.
No, you're writing I.
No, there was a. Oh,
I is intensity to a given frequency.
Yeah, you're ready.
no, but it's just not flowing because the log term was in the radiated cross section.
Yes.
So let me go back to see what I was.
Yes, this one. No, this is the
I was this.
Yes. So you have written that one only. C square by b square beta square. One difference.
Because without
Okay, but now when I integrate it over
Chi
b
is integrated over
squared,
b.
when I integrate it over b db, I got something that involved the log of b min. See, there's no b here, right?
B is there.
Oh, there's still a b. All right. So I'm still working with. So far, I haven't made use of this. All right. You know what? I think here. I was just calculating this. Now I'm going back to IB. And this is still per log omega, so it's still a function of the impact parameter. I haven't integrated over anything yet. And now no, that's not what I want. Select all. Okay. It turns out I'm not going to use turns out I'm not going to use chi so much because since I've already established that the radiation cross section is all right. Okay, here's the thing. If I calculate how much energy is radiated per unit log of omega, it's omega times this. So, all right, I mean, this looks right, but it still depends on B. All right, the number of, but here's the point. The point is it goes as 1 over B squared. So near B min, I'm going to get a lot more of everything. I'm going to get more energy and more photons than if B were large. So in terms of logarithmic intervals, I care most about the interval near B min. I think that's the point. I had to calculate what it was, but whatever B is, this formula is valid. But now if I put B min and calculate the number of photons and the energy in that region of impact parameters, then this was the number of photons per logarithmic interval, the symbol number, which was basically dW divided by h omega. So this expression is just this minus the h, without the h omega, divided by h omega. And this here is a dimensionless number, and I find dimensionless numbers particularly convenient because you have to remember their dimensions. And this is the number of photons that's emitted per log of omega, but here the value for B that I'm putting in is B min. So we can assume that the geometric cross section was about pi times B min squared, of that order. And this is the number of photons I get out. And here's the point. The point is that it's proportional to alpha cubed. For an electron passing by a proton by one, let's say it's going exactly at c over times alpha, so it's exactly the velocity that it would have in orbit. And I just want to know what's the probability that it will be captured, that it will emit a single photon.
Yeah.
Well, it only has to emit one photon at this impact parameter to is that right? Is that right? Let me think. It has to emit an energy of order its kinetic energy to be captured.
Yes.
And we said that B min was defined by the condition that the characteristic photon energy it emits at, which is B over H times B over V.
Yes.
E is of the photon. E is of order H times
B by B.
V over B min, and B min was
H cross by MB.
Yeah, so it's
MB square.
so
it's
it's
of the order of
H over
MB. The H will be cancelled out. MB square.
You're right. H over H MB squared. Yeah.
It will be of the order of the energy, kinetic energy of that electron.
I'm just wondering what is. I think B min is of order the Bohr orbit, right? If V is C over 137, then and otherwise it's smaller.
Yes.
But either way, whatever value you pick for B min, the typical energy that the photon emits is enough to make it get captured.
Yes.
So really, this is the probability of the electron being captured, of the the electron being captured, and it's really the recombination cross section over divided by the geometric cross section of the collision.
Yes.
And the point is, it's alpha cubed, which is a small number. It's like 1 over 10 to the 7. And that's why it's much harder to make new hard photons. I said 1 over alpha, but it looks like I meant 1 over alpha cubed. It's much harder to make new photons than it is to just scatter off. Now this is, by the way, this is the, this is the electron nuclear scattering. It's not the Thomson cross section.
Yes.
But the Thomson cross section, I think the Thomson cross section is also down. The Thomson cross section is some factor of alpha times the Bohr cross section. The Bohr cross section is about 1 angstrom squared, so it's about 10 to the minus 16. Thomson is 10 to the minus 24. So so that sounds also like alpha cubed. I'm sorry, I have to think about that a little more. The point is, leaving aside photon electron scattering, electron proton scattering is much more common than free photon emission. So it's not a simple matter to make new photons. Just because the clouds, just because the electrons and protons are colliding doesn't mean you're going to get a lot of photons in a hurry. But I call it free emission. What I really meant is this is the probability for recombination radiation. Okay, now there's an alternate method for calculating Bremsstrahlung, and it's kind of elegant, and it leads to thermodynamic insight. So So that's what I'm going to do here. And actually, it's the way Peoples does it in his cosmology book.
Oh.
Do you guys need a break or something? Or?
Maybe not. But maybe you don't have much.
What? Maybe a little more?
Yeah.
Well, I'll, you can take a break. I'll huh?
Cosmology book. Which sort of cosmology book can be consulted?
What?
Which sort of cosmology book can be consulted for this?
Which
for
sort
this
of what?
cosmological book you told?
People's physical cosmology. It's just because he needed to discuss brainstorming in the cosmological context, so he needed a quick derivation. Because he likes to explain things, so he didn't just pull the Bremsstrahlung formula out of that. He derives it while he's in the middle of the cosmology discussion.
It's called Feeble.
Peebles. P-E-E.
P-E-A.
P-E-E-B-L-E-S. And I should have a copy of it on my shelf. Not that I'm going to lend it to you or anything, but...
Maybe I have it.
Yeah, it's probably a
It's okay. I'll find it online. On libraries.
But no, but is there some place where you can get new books?
Huh?
New books.
New books. They said that new books were in some conference room.
Conference room? There's a seminar room. There are also books over there.
Where? Which?
The seminar room. Downstairs.
You won't find.
No. No, I ordered a new book, and they said it's in some conference room somewhere. Maybe. Okay. Anyway, you want to take a break and then we'll meet in 10 minutes?
Yeah.
Okay. Why is it not cold? I don't understand. Why is it?
Temperature is 27.
Oh. Okay. Got another book by Demon Nath. That's it. Okay. So,
He sent you or you got it from library?
no, I ordered from the library. Alright, anyway, here, the alternative method is actually very simple and elegant. You just say, okay, electrons have thermal velocity mv thermal squared over 2. If I impose an electric field, the electric field makes them oscillate and pick up an additional term on the average. Since the electric field is randomly oriented relative to the original velocity, then it's just small amount oscillatory motion. Well, we know it's just a driven oscillator with zero frequency. It's just the amplitude is proportional to 1 over omega squared.
Where's omega here?
Here. This is the amplitude, the added kinetic energy due to the oscillatory term forcing of the electric field.
Which one is the amplitude?
This is the velocity.
Yeah.
And it's the
Frequency of that.
no, the amplitude. When I say amplitude, I mean in velocity.
Oh, really?
This is the extra velocity that it has in addition to 3/2 kT. And the question is, when is this actually converted to heat? As long as it's oscillating, it's not yet heat. But every time the electron collides, you assume this amount of energy is converted to heat. At that point, the electric field, at that point the light that made the electric field is hereby absorbed and converted to heat. Until then, the oscillation of the electron is part of the wave.
Yes.
The wave is still the wave, and it's only damped at the collision frequency. So this amount of heat is damped every collision time. And what's the collision time? Well, the collision frequency, the collision cross section is pi r squared, and this is just the Bohr cross section. It's just electron on the nucleus, say, or another electron maybe. But no, that wouldn't help you because the electrons oscillate together in phase, whereas the nuclei are going in opposite direction. So you want collision with the nucleus so that the momentum is really scattered. If the two things are oscillating together, they exchange.
Yes.
They haven't gotten rid of anything. Okay, so this is the energy density of the oscillatory motion, and sigma nv is the collision rate. So together it's the rate of collisional absorption, and if I write it in terms of the wave energy density, wave energy flux, it's E squared over 8 pi c. Actually, if I counted the magnetic field, it would be 4 pi. So maybe this should.
This is the
But no. But if I counted the magnetic field, there'd be an additional B squared over.
Then the total electric
But since I only counted the electric field in the figuring, it's kappa. Kappa is the opacity, and that tells opacity times energy flux is rate of energy absorption per unit area. Without the C here, it would be per unit volume. With the C, it's per unit area. But this is the definition of opacity. And the emissivity, if I go up here, is basically the net opacity times the intensity.
This J.
I'm not sure. Wait a minute. I'm not sure this C should be on the outside. This is the beam intensity. This is the net opacity. This is the. Oh, I see. This C really. I could have put it here. And then this would be per unit length, the rate of change per unit length, and that's really how opacity is defined. It's the rate of change of flux per unit length. If it weren't for these little details, right, you could just read it in the book, but then you wouldn't. It was per unit. Anyway, so this has this has units of rate of energy density absorbed, because U is energy density. And I think this C is just because kappa is defined per unit length, and this is per unit time. And if I took the C here and moved it here, I would get the rate of energy loss per unit per unit volume per unit length, which wouldn't make any sense. Anyway, here's the question now. Here's the subtle point. I've just derived emissivity. I have an expression that tells me what kappa is. See, this E squared here and here cancels, so kappa is just this expression minus, it's squared over 8 pi. Here I can move if I move the 8 pi here, I isolate the kappa. Anyway, so since I know kappa and I use Kirchhoff's law to relate the emissivity to absorption, then I've derived the emissivity. But the question is that emissivity spontaneous emission, or does it include the stimulated emission?
It includes stimulated emission.
Why?
Because your external electric field. So you have put it basically.
Yeah, but the emissivity let's go back. The emissivity was not proportional to the intensity, whereas the absorption was proportional to the intensity. Now the intensity is proportional to E squared, but we canceled out the E squared. We just got the opacity, which is independent of intensity, and we related that to the absorption, which is... So the question is, does this expression, is it just stimulated emission, or does it include, is it just spontaneous emission, or does it include stimulated emission?
Spontaneous emission.
You think it's just spontaneous?
Occurring the emission.
Okay.
Just because
Now I have to admit, I forgot. I forgot.
Yeah.
But I think that you're wrong and that it does include stimulated emission, uh, uh, stimulated, stimulated absorption.
No, I said spontaneous only. No,
Right.
I
And
said
I think you're
spontaneous.
incorrect and that it does include stimulated. Why? Because what I derived was the total. I derived the total amount of heat absorbed. And and I didn't say, I didn't say and it was a classical calculation. And it was proportional to the electric field. Anything that's proportional to, this is what I derived, and it was proportional to the electric field. Now I slightly threw you off the track when I said I was canceling out the electric field. That's just to get the definition of opacity. But the emissivity, granted, it doesn't include the radiation that I imposed, that I shown on the plasma. That's not part of the. Wait a minute. You know what? I'm still not sure. I just know it's the total amount. That's absorbed. I know that in thermal equilibrium, the total amount that's absorbed is equal to the total amount that's emitted. And when I say total, I mean total. It includes the stimulated emission. Now, here's the thing. In thermal equilibrium, for most modes, I typically have one photon in the mode, so there's not that big of a difference. But when h nu is much less than kT, then I have a lot of modes. And then it makes a difference. So the point is, if I calculate this expression, I get 0.4. If I do a more exact calculation, I get 1.93. But since it's a classical calculation, it's only valid for h nu much less than kT. So it includes stimulated emission, but since it's a purely classical calculation, it doesn't include spontaneous emission, which means it's only correct when I have a lot of photons. Now, this is the exact calculation. Peebles does not actually, I copied it from Peebles, but he doesn't derive the quantum mechanically, he only did it classically. But note that this expression equals this expression, except for the 1.93 instead of 0.4. But it equals this expression when h nu is much less than kT, because then this expression is just h nu over kT. But when you write it exactly, this is done with quantum mechanics. You see that it's the stimulated emission minus the stimulated absorption, because this is the ratio of the states, of the final and initial states of the electron ion system, and that means it's stimulated emission minus stimulated absorption. So the spontaneous emission was just for that one extra photon. It's just purely quantum mechanical, and it has nothing. When h nu was much less than kT, I had a lot of photons anyway in thermal equilibrium, and stimulated emission. Not only was stimulated emission included, but spontaneous emission was not included. And any time you see any classical calculation in any instability, any plasma instability, like you have an electric field and it grows because of the plasma's unstable and amplifying the field. That's all stimulated emission. Any classical effect is stimulated and not spontaneous. Okay, so now we're up to inverse Compton. I think we've been going for how long now? Is it this computer is correct.
Yeah.
So it really is 4:30. And we should have started at 2, so
We started 2:30.
yeah, but
No, you sent email by 2:30.
what?
Yesterday you sent email by 2:30.
I said it starts at 2:30?
Yeah, you sent so.
Oh, right.
That's why I
You're
didn't
right,
come.
you're
That's
right,
why
you're right.
I thought I'm gonna come by 2:30.
Okay, so we need to do another half hour because we took a 10-minute break at least. So we need to do at least another 45 or 50 minutes.
About to finish.
Well, this is a new. I can finish this. The total emission rate ends up being this,
Yeah.
and it's 10 to the minus 27 ergs per cubic centimeter per second. I think this unit is actually wrong because I think it's plus. I think it should be plus because this down here should be the rate of energy emitted. I can look it up. It's the rate of energy emitted per unit volume per unit time. Now it depends on the square. Why does it depend on the square of the density?
Square of the density. Dimension.
No. Why should the rate of emission and free emission depend on the square of the density? Because it's proportional to the collision rate, and the collision rate is per unit volume is proportional to the. See, that's the point. That this is per unit volume, not per particle. Per particle, it's proportional to the number of targets it hits, which is density. But the total number of emitters times the total number of targets is proportional to the density squared.
You're talking about collision between electron and proton.
Yes,
Right?
yes, electrons and protons.
And that collision rate is proportional to square of density?
Of course, per unit volume. The number of collisions per unit volume is proportional to the square of density because it's the number of colliders and times the number of collidees.
Yes, same number.
So, so here's the thing, I gave enough homework for 1 week, and I want to give more homework. Let me just make sure these units are correct. Radiation.
Which book is this?
What?
Which book is this?
Same as it's called astrophysical constant. Astrophysical quantity, sorry. I give up. Going to the radiation
See,
here,
from
absorption
internet,
by
internet you
particles.
can get.
What?
From internet, the Wikipedia or something like that.
I know.
It's a story.
Free absorption emission 43. What is
Like,
it? Yeah, yeah, I think that this formula here means that you take n in particles per cubic centimeter. Because it's ergs per volume per time.
Yeah. Yep.
But any
So if it's per
any
so if it's per time, then is inverse one only here.
yeah. See, he gives NE and NI in
This would be AC inverse one.
in inverse cubic centimeters.
And
So
also second will be minus S inverse one. It's per unit time.
right. So this should be per minus 1. And now if this, since I wrote small n here, the units are a number per centimeter squared, per centimeter cubed, which means that if I keep these units in here, then this should be a plus, so that when I multiply it by centimeter to the minus 6, I get per unit volume. So I clearly copied this out of Allen, but I forgot that here I'm using n to mean density. Here his ends were capital, and he actually had there's a centimeter to the minus he already had the units of centimeter to the minus 3 in here, so there's actually centimeter to the plus 6 implicit in this.
Because he's using dimensionless density.
That's right. He was using dimensionless density, which, and I'm not. But the point is, after when you're finished, the bottom line is it has to be per unit volume. So if you have a cosmic plasma, it should be okay. Now there's one more way I want to derive Bremsstrahlung. I actually taught it to the undergraduates, but I think you guys should do it. Why don't we meet tomorrow for like a half an hour?
Yeah.
Like 2:30 to 3 before the colloquium.
Okay.
And yeah, now a word about the homework. You don't learn by sitting in class, you learn by calculating. So the homework is far more important in these lectures. So I'm serious about it. I want to see the homework done. And that's really all I care about.
Sorry.
No, we're just finishing this time.
When you're done, bring me up.
No,
I'll wait here.
no, I really am finished. Get out of here, you guys.
Okay, getting out.
So you guys can take a hint.
Do you want me this? They'll need it. Just keep
I
bringing it
still
to
need-
class.
Yeah, okay.
I can manage without it.
I'll-
I can manage without it.
But I will buy my laptop in December. I'm going to 10th of December.
Well,
So after that, or maybe you can take it before that.
right.
Just
You
let
can.
me
You
finish
can.
the paper and then you can take it because I still need to make figures. And
Yeah.
it's much
Okay.
easier.
All right. Right. So you take this, and I'm gonna. I was gonna do it today. But I'm going to order a Macintosh 11-inch. What are they called? Like an Air.
There are two, Air
Air
and Pro.
two.
Air and Pro is there, but Pro's core is nearly 2.6 gigahertz gigs, i7 or i5. But Pro Air doesn't have. Air is probably 1.6 gigs.
No,
or
no,
something.
you can order it with a 3.2 gigahertz chip.
Yeah, it could be turbo boost to 3.2, but you have
For
to do
you
that.
pay
but,
more.
But you have to check that whether it is core i7 or i5. I mean, otherwise.
Are you ordering for yourself?
Yes, I'm ordering for myself.
Probably still money for that.
Yeah, but I don't want to wait until.
You can buy some other laptops like this. It's much cheaper and way better.
This is better.
No, this is also much better.
No, this is better.
Than MacBook Air, yes.
Mac Air?
Yeah.
Really?
Yeah, because now you see that they have good processor and good everything. And
Yeah,
you can write on the screen. That's bigger
but
advantage.
maybe I'll get a new one. But I didn't like this. I don't like this.
But in MacBook Air, you cannot write on the screen.
You
MacBook
cannot.
Pro.
Yeah, you can write on a separate screen.
Yeah. The thing is, anything you buy from Apple in Israel is very expensive.
Right. Yeah. All
That's
right.
not
Look.
mine.
So maybe I'll just grab this from you. That would be the best thing.
Maybe you can just wait for a month. Or no, I can take it actually before that. I will buy my own.
December 10th. Yeah, that's only another month. Maybe I can survive. Ori, I'm really finished.
You're going to India?
What? No,
US.
I'm going to US.